All right, 2.2, energy bar charts. I also call these things LOL diagrams. You'll see why I call them that in just a second. So you see I've got up here LOL diagrams. We're going to use these things to represent the role of energy in a physical change. We have yet to discuss or define what a physical change is, but I think I can do that quickly. A physical change is just when a substance changes form, like it goes from ice to liquid in case of water. It's totally separate from a chemical change. A chemical change is when a substance actually changes chemically. So when we have gasoline in our gas tanks and it combusts to form carbon dioxide and water. So it totally turns into something new. With physical changes, we can usually easily get the original state back by doing something, in the case of water, by just refreezing it. All right, so let's talk about energy bar charts, and here's why we call them LOLs. If you can't see it already, we've got an L, an U, and an L. There we go. So that's why it's called an LOL diagram. So let's construct an energy bar chart. This is what they all look like in this white box right here. We're going to consider a specific example to kind of highlight this white box. We got a cup of hot coffee. And we take that cup of hot coffee and it's cooling as it's sitting on the table. Okay. We want to think about what's happening to the energy flow in that instance. So first of all, we want to determine what's in the system. The system is the object that we're talking about. So in this case, our system is going to be the cup of coffee. So we're going to go ahead and take the thing that's inside of our system, that is our system, and we're going to place it into the O in the center of the energy diagram. The surroundings is going to be everything else. So the system, the cup of coffee, is going to be either losing or gaining energy from the surroundings, which would be like your kitchen or wherever it is you're drinking your cup of coffee, out on your front porch when it's negative 15 degrees outside. So that's everything else. Everything else makes up the surroundings. All right, so we've determined our system, it's a cup of coffee. Everything else makes up our surroundings. We good? Awesome. So that's really like step number one. Here's step two. We need to decide whether ECH is involved. ECH, what was that? Chemical energy. Yes, very good. Okay. So in this case, we're going to start with coffee and we're going to end with coffee. It's still coffee. Now, I don't like drinking cold coffee. I like drinking hot coffee, but at the end of the day, it's still coffee. It's not something new. It is not as though I put my coffee mug on my table and it turns into, I don't know, rubbing alcohol. That'd be horrible. No, it's coffee. So there's no chemical change going on. So we are not rearranging any molecules to form any new substances. So in this case, and for the rest of this chapter essentially, we can ignore ECH. We'll come back to it later on in the semester. Next, let's assign some values for EPH. What was EPH again? Yeah, phase energy. That's right, phase energy. Now, due to interactions between the particles, the energy stored due to the arrangement of the particles is ranked as follows. Solids have less energy than liquids, and liquids have less energy than gases. If we want to think about what's the most energetic, this guy is the most energetic right here. So the most, that's a horrible color, most energy on that side. What's got the least energy? Solids. Should make sense, right? Because the gas molecules are moving around a heck of a lot faster than the solid molecules. All right, so we have assigned each one of these phases a certain energy ranking. In our energy diagrams, we're going to choose to represent these phases by using solids, 1 bar, 2 bars for liquids, and 4 bars for gases. And now, let me give an idea of what that looks like. So I'm just going to draw the initial state of an energy diagram. So let's just say that this was, a second here, ETH on this side, and then EPH right here. EChem would be to the right of these two, but we're not going to put it in. All right. And then we've got these bars. 1, 2, 3, 4. 1, 2, 3, 4. Okay. Now we're just talking about E phase. Now if we've got a solid, that means that the bar that associates with the solid is only going to be that tall. It's only going to have like 1 bar is what we're saying. A liquid would be 2 bars. It would be a liquid. Gases would be 4 bars. You might say, well, why not 3 bars? That's because gases are so completely different than liquids or solids because their molecules are so far apart. Like the molecules between solids and liquids are kind of different. You know, the liquid molecules are a little bit further apart. But between liquids and gases, the gas molecules are exponentially more far apart than between solids and liquids. So that's why it gets 4 bars. Okay? So there, we've just assigned values for phase energy. Now, let's go back to our coffee cup example. We're going to use 2 bars because coffee is a liquid. I don't like drinking solid coffee or gaseous coffee, so it's a liquid. So in our initial state, you'll notice over here it says initial. Okay, this is like when it's hot, you know, you take it out of the microwave or you just pour the cup out of the carafe and you set it on the table, it's hot. So that's our initial state. So it's energy in the phase. Okay, so it's going to be liquid. So this is the L. Let's get 2 bars. All right, now we can actually go over the other side, the last L. The coffee is staying liquid. All right, it's going to get hot, it's really warm, but as it cools down, it's going to stay in the liquid state. So our phase doesn't change. Now you might say, well, wait a minute, Cornica. We can see steam coming off, and there's some liquid evaporating, so there's water evaporating into the gaseous phase. Yeah, a really little bit. And in fact, as that coffee cools, it's going to even be less and less and less of those molecules going into the vapor state. So we don't even have to talk about a phase change. It's liquid coffee at the beginning, it's liquid coffee at the end. So 2 bars on the left, 2 bars on the right. All right, so phase energy in this case is not that difficult. Thermal energy, on the other hand, might be tricky. All right, let's go back to our phase. There's our phase, and there's our phase. Now, look at how many bars I toss in there for E thermal. I'm going to toss in 4 big bars. All right, only 2 bars at the end of the day. Now, you might say, well, how do you know to place 4 bars in for E thermal at the beginning and 2 at the end? I think you're all going to say, well, yeah, it's hotter at the beginning, so there should be more bars on the left than there are on the right. But how do you know 4? So we have to set some standards. All right. We're going to use 4 bars for hot coffee, 2 bars for room temperature coffee. Other values might work, but we want to be consistent. Now, I want to set the following standard, so we're all kind of on the same page, right? So 4 bars, we're going to call this 4 bars, okay? That's going to be like scald. Sorry about that. That's going to be like scalding, okay? You spill that on yourself, you're going to know about it. Okay, 3 bars. 3 bars. Hot tub in it. All right, hot tub in it. All right, 2 bars. 2 bars. Room temp. Okay. 1 bar. I know I'm all over the place here. 1 bar. Chili. Chili pickles. All right. This is chili stuff. You put your hand in there. You take it out right. This is like Lake Michigan in June. Okay. Cold water. Right. All right. Certainly lower than temperature. Right. So 4 bars scalding, 3 bars hot tub, 2 bars room temp, 1 bar chili. Anything below 1 bar. So we could call this like less than 1 bar. Okay, now we are in a different state. Anything lower that's less than 0, less than 0 degrees C. Okay, and we'll get to that in a little bit. All right, so remember, these are all, everything that I have here in black writing, okay, everything that I have here, that guy, that guy, that guy, that guy, and that guy, these are all for what? E thermal. Thermal. Okay. All right, so our final situation has 2 bars less than our initial situation. So if we take a look at this, our final situation, the one on the right side, okay, the one right over here, there are 2 bars less, like these little bars are voided, than there is on the left side. There's 2 bars more over here. That energy has to go somewhere. We learned that energy can't be created or destroyed. So here's where our energy transfer mechanisms come into place. Remember, these are our energy storages. These are our accounts. Okay, and now we're going to see how our energy transfer mechanisms come into place. Well, how does coffee cool? Well, heat leaves coffee, so heat gets transferred from the coffee cup to the surroundings. So we're going to place the 2 bars that we lost. Okay, we're going to stack them on top of each other. We know that the coffee cup is getting colder, so the heat must be leaving the coffee cup, so the arrow is going away from the coffee cup. Okay, and how is it going away? Well, it's using the energy transfer technique of heating. It's just heating the surroundings. So don't think of the coffee cup as getting colder. think of the coffee cup as actually giving its heat to the surroundings. So if you get like a really sensitive thermometer inside of your kitchen, you would notice that your kitchen temperature increases a little bit because of the coffee. Interesting. All right, good stuff. Now, let's consider a phase change because it gets a little bit crazy now. All right, we got a tray of ice cubes. All right, tray of ice cubes, you make some Kool-Aid. You take it out of the freezer, place it on the counter. Obviously, the ice cubes melt. They become water at room temperature. All right. So let's think about what do we know about this situation. A, the system, the thing that goes in the circle, in the middle of the energy diagram. The system is the tray of ice cubes. B, the solid water turns to liquid water. It's water. There's no change in chemical energy. Okay, so we can totally forget about chemical energy. Awesome. C, ooh, phase energy is going to increase. We're not going to have the same phase energy on the left as we do on the right. Interesting. Why will it increase? Because liquid molecules are more adventurous, more energetic than solid molecules. Good. The thermal energy is going to increase, obviously, right? Out of the freezer, into the room temperature kitchen, boom. All right, now, let's take all these ideas, A, B, C, and D, and let's represent this using the LOL diagrams. Ready for this? Choice of bars for E thermal is arbitrary but consistent. By arbitrary, it's like if Jorge wants to use one method, and Wyatt wants to use another method, and Ellen wants to use a third method, as long as you're consistent. You know what? That's really hard for me to figure out. So use that method that I showed on the previous slide. Try to be consistent with everybody in the class. We generally use 2 bars for room temp and 1 bar for cold water. So, -8 degrees Celsius, which is what I said the ice cubes were at once they were in the freezer. Holy man, that's really cold. So that should be less than 1 bar. Remember on the previous slide, I said less than 1 bar is less than 0 degrees Celsius. So here we go. Check it out. On the left side, in the initial, when the ice cube tray is in the freezer, this is the freezer over here. Okay, your E thermal is really low. Why? Because we have a low temperature. Should it be 0? Heck no. It's not 0 unless we reach absolute 0, and that's not happening. Okay, so it's less than 1 bar. We put it like half bar. Phase. It's a solid, right? We said that solids get 1 bar. Awesome. Let's skip the circle for right now. We'll come back to that. Okay, it warms up, so it gains energy, turns into a liquid, so it gets 2 bars. And now the phase changes. It goes from the solid to a liquid, becomes more energetic, so it now has 2 bars. So let's do some math. We have 4 bars here. We have 1.5 bars here, right? So we are missing 2.5 bars. Those bars have to come, or have to be located in this middle section right here. And that's what we're going to do right now. Okay? So here we go. We have 1 bar. We have 2 bars. We have a 3rd bar, but it's only half a bar, right? Ooh, there we go. Beautiful drawing, Kornick. All right, now, tricky question. Where's the arrow point? Did you get it? Points into the ice tray, right? Yeah, because the ice tray is absorbing the heat. So it's heating again. Okay? We awesome? Awesome sauce? Good. So it's got to flow into the system. That's what she looks like at the end of the day. Good? Super. 14 minutes. That is great. Thank you for paying attention. I love it. See you tomorrow.